right, I think we are live. We're going to give people just a second to log in here as we get started. So those of you that are logging in right now, welcome, welcome. We're going to get started here in just one moment. We're giving people a chance to log in. So a big hello to everybody who is logging in right now. We are excited to have you here for Cheg's live office hour. This is your office hour to help you be successful in your trigonometry class. We have lots of lives going on with Cheg, so make sure you're scanning this QR code up in the corner so you are aware of the schedule. We're covering chemistry, we're covering physics, economics, all sorts of stuff. So make sure you're joining us. For those of you that have been here before, welcome back. We're excited to have you back as we're going to dive into some trig concepts. For those of you that are new here, this is your office hour. You can think about this as the chance for you to get your questions answered. So make sure you are dropping all your trigonometry related questions in the chat. That might be trig proofs, trig properties, the unit circle, how to remember the unit circle. That might be trig equations. That might be inverse trig. All sorts of trig problems that we're going to look at today to help answer your questions. And to get started, we're going to start off with a proof because everybody loves a good trig proof. So let's start off with this trig proof. We're going to prove that secant squared of theta over 2 minus the secant of theta is going, secant squared theta, we'll say, is going to equal the secant of 2 theta. So how do we prove this? There's a couple ways to go about a proof like this, but one of my favorite trig proof methods, if you don't know what to do with trig, like tangent, secant, cosecant, what I want to do is change everything into sines and cosines. So secant is the reciprocal of cosine. So secant squared is 1 over cosine squared. And so we've got 2 minus 1 over cosine squared as well. Now, when you do this trick, almost always you're going to end up with these little fractions inside of a bigger fraction. And so our strategy to get rid of those little fractions is we're going to multiply every term by that least common denominator of cosine squared on top and bottom of the fraction. Of course, this cosine squared has to distribute all the way across, so I'll go ahead and write the cosine squared there as well. And when I do, these cosine squareds reduce out, those cosine squareds reduce out, and I'm left with 1 over 2 cosine squared of theta minus 1. Now, with the proofs, the key is being able to recognize those formulas when we have them. 2 cosine squared minus 1 is one of our trig identities that we should at least recognize and be able to look up on a trig identity worksheet. 2 cosine squared minus 1 is cosine of 2 theta. So this is 1 over cosine of 2 theta. And what's nice about cosine is the reciprocal of cosine. 1 over cosine is equal to the secant of that angle. And secant of 2 theta is actually what we were looking for. And so we'll put a little black box on it. Okay, it's a little orange box, but this is Cheg. We do orange instead of black. But you can also write QED if you prefer the Latin. I had one professor once write W to the 5th, which stood for which was what we wanted. Either way, that's how I'm going to attack this trig proof. And I already see a lot of great questions coming in the chat. So if you have more questions, please stick them in the chat because this is your office hour. If you want to see more proofs, stick in the chat that you want to see more proofs. I see lots of great comments about looking at degrees, minutes, and seconds and trying to understand what those are. So let's break that question down. Thank you for dropping that in the chat, and then we'll kind of continue working through. I see lots of other great questions related to trig as well. So degrees, minutes, and seconds. So if you think about it like a clock, there are 60 seconds in 1 minute, right? And 60 minutes makes up 1 hour. Well, we don't have hours, we have degrees. So the idea is if we want to be more specific than 1 degree, we can break it down into minutes. And so what you might see something is we've got an angle that's 48 degrees, 15 minutes, and 25 maybe seconds. And so you'll see stuff written like this. Basically what that means is the 15 minutes, in addition to the 48 degrees, the 15 minutes are 15/60ths of a degree. And then the 25 seconds, well, if there's 60 minutes in a degree and 60 seconds in a minute, 60 times 60 is 3,600 seconds in 1 degree. And so we would add this up. I don't have a calculator right on me right now, but if you just added those up, that would give you the equivalent angle in degrees. So minutes just breaks a degree down into smaller pieces. Seconds breaks a minute down into smaller pieces. It's really big when we're talking about really big round things. This comes up a lot in things like astronomy, because in astronomy, sometimes we're talking about the Earth. And the Earth is really big. And so rather than just talking about 48 degrees on the Earth, 48 degrees spans quite a bit of space. But if we break it down to minutes, that helps us as well. And then we start talking about big things like Jupiter or the sun or some of the big stars out there that dwarf our star completely. Going down to minutes can help us see more accurately what we're working with in there. So that's the idea of degrees, minutes, and seconds. It's just a way to break it down really into a fraction instead of into a decimal. So many great questions coming in the chat. I'm going to try and keep up with them. I love to see this excitement about trigonometry and seeing you log in, and so excited to learn about it. Tell me where you're logging in from. Stick in the chat where you're logging in from. I want to see, is there anybody from what states, what countries? I am excited to see that. Explain the limits of trigonometry. Ruby loves you for, can you be a little more specific what you're looking for? Are you talking about like where the asymptotes are, or like the fact that sine and cosine are between -1 and 1? Or are you talking more of like a calculus question? So with limits on trig problems. So give me some more specifics so that I can dig into that. We got a little computational problem from Instagram. Sine of 60 plus the cosecant of 678. That's cosecant of 678. Let's see what we can do with this problem. I'm not sure exactly. I'm worried that that 678 is a typo of some sort, but we'll work with it and see what we can at least simplify and what we can learn from this. So one thing that we should know is the sine of 60. We can find that point on the unit circle because sine is just the y coordinate. So if I have a 60-degree angle coming up to here, the y coordinate here, that long distance is going to be √3/2. That's that height. So the sine of 60 is √3/2. The cosecant's not quite as obvious. The first problem with the cosecant is this huge 678. We're going to go 678 degrees. Well, one lap around is 360 degrees. We're still not there. So let's do another lap around. 2 laps around, that's 720 degrees, isn't it? So we passed it. So it's going to be less than 2 laps around. Let's see what we get when we subtract 360 from this. 8, 7 minus 6 is 1, 3. So 318 more degrees. So that's going to be 318 more degrees. This is 270. So 318 is going to be somewhere around here. And cosecant, remember, is the reciprocal of the sine of this 318-degree angle. So if I was on my calculator, is really the only way I could probably do this, is I'd have to put this in my calculator, 1 divided by the sine of 318, and then we could add it to the square root of 3/2, because that's what the sine of 60 is. Square root of 3/2, I said. But that's about all I can think of to do with that one, unless you're looking for some other property there that I'm missing. Okay, you want to see the Angelina on Instagram wants to go over the cosine difference formula and the cosine sum formula. So let's see if Whoops, dropped my pen. These pens are slippery. Watch out for that. The sum and difference formulas. I think you're talking about this formula that says the cosine of alpha, you said difference, so cosine of alpha minus beta is equal to the cosine of alpha cosine of beta plus the sine of alpha sine of beta. There's also a couple other formulas that are related to it. So we could do the cosine of the sum. Cosine of the sum would be the cosine of alpha cosine of beta minus the sine of alpha sine of beta. Then we've also got the sine of alpha plus beta. That is the sine of alpha cosine of beta plus the cosine of alpha sine of beta. And then we've got the sine of alpha minus beta is the sine of alpha cosine of beta minus the cosine of alpha sine of beta. So those are the formulas. I don't know if you want me to prove them. Proving these is actually pretty ugly geometry proof. It probably takes me about 20 minutes to go through the whole geometry proof and really explain it well. But let's see if we can do a proof that's going to use one of these properties. Let's see if we can prove that the cosine of A plus B plus the cosine of A minus B is equal to 2 cosine A cosine B. All right. Well, all I have to do here is use the cosine A plus B formula. That's this one right here, which is going to break it down into something that we can work with. So the cosine of A plus B is the cosine of the first thing, cosine of the second thing, minus the sine of the first thing, sine of the second thing. And then we've got a plus. Probably should do that in blue. Then you see we've got this cosine of alpha minus beta. That's that difference formula that you said you wanted to work with. So that difference formula says we take the cosine of the first thing times the cosine of the second thing plus the sine of the first thing, sine of the second thing. And what you might notice about this expression that we ended up with is we've got some like terms. We've got a negative sine A sine B and a positive sine A sine B. Those are going to go to 0 when we subtract them together. Then we've got a cosine A cosine B and a cosine A cosine B. One of them plus one of them gives me 2 of these cosine A cosine B's, which was what we wanted. We'll go with QED this time to finish out that proof. So that's kind of how we can use those sum and difference formulas to get at proving various new identities. Excellent. How can I learn all these trig equations? MEHTAB_1. How do you learn all these trig identities? That is such a great question because there are a lot of trig identities. I've got a little cheat sheet here. Just look, all of those identities. How are you going to learn all of those? There is a ton of them to keep track of. The best way to get to know them is first off, start to look at how they're related to each other. So one trig identity you should know. This is the most important trig identity. So take the time to learn that sine squared plus cosine squared. What does that equal? You type it in the chat. What does that equal? You should know this one. Anyone putting it in the chat? What does sine squared plus cosine squared equals? Hopefully you said 1. Sine squared plus cosine squared equals 1. Because sine is the y coordinate on any triangle. Cosine is the x coordinate on any triangle. And it's a unit circle. And so when you do the Pythagorean theorem, a squared plus b squared equals c squared. You should know sine squared plus cosine squared equals 1. The other thing you should know are your reciprocal identities. So you should know that secant of theta is the reciprocal of cosine. You should know that the cosecant of theta is the reciprocal of sine. you should know that the cotangent of theta is the reciprocal of tangent, or even better yet, it's just cosine divided by sine, because you know that tangent is sine divided by cosine. One thing that helps me remember the reciprocal identities is cos cannot go together. So if I've got a cosine, it's not going to be the reciprocal of a co, it's going to be the reciprocal of the secant. Sine goes with cosecant. Cotangent goes with tangent. No two cos go together, and no two non-cos go together. So that kind of helps me keep track of what this is here. Those are really the formulas you need to know. Now, there are other trig identities that you can pull off of this if you know how they work together. For example, if I were to divide each of these terms by sine squared of theta all the way across, sine squared divided by sine squared is 1. Cosine squared divided by sine squared is cotangent squared. Remember, we talked about cotangent as cosine over sine. And 1 over sine squared, remember sine, it's going to have to go with a co. That's equal to the cosecant squared. And so we've got this other Pythagorean identity that 1 plus cotangent squared is cosecant squared. And I don't actually have to memorize that. I just know I take sine squared plus cosine squared equals 1 and divide by sine squared. If I divide by cosine squared instead, I would have sine squared divided by cosine squared, which is tangent squared. Cosine squared divided by cosine squared is 1, and 1 divided by cosine squared is secant squared. And that gives me the other trig identity that I might need to know. So you don't actually have to memorize them if you know where they come from. So that's my tip for learning the trig relationships. Know their connections, know their relationships, and then just start to practice using them. Do those trig proofs. Do the solving with trig. Play with the properties so you start to get to recognize those properties. So we did that proof a second ago, a couple examples ago, where I saw 2 cosine squared minus 1. I know 2 cosine squared minus 1 is something. That should flag in my head. That one's familiar. You might have to still look it up, but that might be helpful for learning those trig relationships. All right. Brody on TikTok wanted to know about doing more proofs. You can never do enough proofs. That's probably the most common question we get. So let's do another proof just to keep practicing working with proofs. Let's try this one. Let's prove that 1 plus cosine of theta over the sine of theta plus the sine of theta over the cosine of theta is going to equal cosine theta plus 1 over sine theta cosine theta. We're going to prove this relationship. Excellent. More proofs. Always want to do more proofs. Thank you, Brody, for the question. The way we're going to do this is we're going to pick one side, the more complicated looking side, and see if we can simplify it to make it look like the other side. Well, what I notice in this one is everything is already in terms of sines and cosines. So I can't do any changing there. The other thing I can do, though, is big picture, I'm adding 2 fractions. Think about adding 2 fractions. What do you need to add 2 fractions? That's right. We need a common denominator. The common denominator here is going to be sine times cosine. So I'm going to multiply this one by cosine theta on top and bottom. And I'm going to multiply this one by sine theta on top and bottom. So that I have, after I distribute, cosine theta plus cosine squared of theta plus sine squared of theta over my common denominator, which is sine theta cosine theta. Did I write the problem down wrong? I might have written the problem down wrong. I did not write the problem down wrong. All right, let's keep going. Let's see what we get. Oh, no, I'm good. I'm good. I made a mistake in my mental math. We're good. All right, so then I can look at this and say, is there anything else I can do with it? And something on here should jump out at us. It's the trig identity that I told you just a minute ago is the most important trig identity that you know because it comes up so often. Did you see that sine squared plus cosine squared? When I see sine squared plus cosine squared, I need to know that that is equal to 1 over sine theta cosine theta. And that is what we were looking for. I'll go back to the little black box, so the orange box for Chegg, because this is Chegg's office hour to answer your questions about trigonometry. So I see lots of great questions coming in the chat. If you have questions from your trig class, stick them in the chat. We're going to do our best to answer as many of these questions as we can in this hour. We're here every week to answer your questions, not just with trig, but we've got other office hours throughout the week. So make sure you're scanning this QR code up here in order to have the schedule so you can keep up with us. Excellent. So let's see what we have. Any good questions? Martina says we're solving for the missing side of a triangle given one side and one trig value. Oh, these are some of my favorite questions. So Martina, thank you for that question, because I would love to do one of these. These are fun. This is something where I tell you, like, the sine of theta is equal to 3/8. And I'll even tell you that, let me see. Should I use the example that you get? Yeah, the sine of theta is 1/8, is 1/2. You said 1/2. Okay, we'll do the 1/2 that you said. And you're given one side length. For the example, A is equal to 20. So you're talking about the sine of A is 1/2, and A is equal to 20. So let's draw this triangle. This isn't quite the problem I was thinking, but it's a fun one. So let's take a look at it. So let's say this is theta, or this is angle A. And then the opposite side then is 20. So lowercase a. 20 is equal to this side on A. If I were to make a right triangle here, the sine of this angle, you have capital A for both of them. So I'm a little thrown off about which one's which, but I think this is right. How can we get at that? What are we solving for? Missing side of a triangle. Do we have another angle? If the problem gave me another angle, we could use the law of sines, which I think is what's missing here, is the other angle. So if I know that the sine of A is 1/2, I can figure out what A is from the unit circle. So I think about my unit circle. Sine is the y coordinate. So the y coordinate is up here. It's probably pi over 6 or 30 degrees. So let's call that a 30-degree angle. But we still need one more piece if we wanted to use the law of sine. So I'm going to give another side. Maybe we don't have the full information. Let's say I've got this side is 10. And we're going to find this missing side over here of x. To do that, we're going to have to use the law of sines. First off, though, I need to find one more angle. And the law of sines allows us to take an angle and its opposite side, and another angle and its opposite side where one of those things is unknown. So I'm going to call this y here. And then we're going to take the sine of the 30 degrees and put it over the opposite side, which is 20. And then that's going to equal the sine of this angle, which we don't know y, and put it over 10. Now, the sine of 30 degrees, we already know is 1/2. That's the angle we were talking about. So I'm going to make this 1/2 and multiply both sides by 10. Well, I might just put this all in my calculator. 10 sine of 30 over 20 is equal to the sine of angle y. Well, we're going to need a calculator for that. Give me a second. I'll pull out my calculator, see if I can do that. 10 sine of 30 divided by 20. Make sure I'm in degree mode. I'm getting 0.25. So the sine of y is equal to 0.25, which means y is going to be the sine inverse of that 0.25. Undoing that sine operation. So if I do the sine inverse of 0.25, I find out angle y is actually 14.5 degrees. So this angle is 14.5 degrees. And I know there's 180 degrees in a triangle. So we can take the 30 degrees and the 14.5 degrees, subtract it from 180. And this last angle, I told you I'm dropping pins all over the place. This last angle then is going to be 135.5 degrees. Then we can do the law of sines again to find that missing side that we were looking for. So let's say we want to do this angle and its opposite side. So we'll take the sine of 135.5, put it over the opposite side, is equal to, we can use any combination. Let's just use the 30 and the 20. The sine of 30 over 20. And then we can solve this by multiplying both sides by x and the reciprocal of this one to get rid of it. So when I multiply by 20, we get 20 sine 135.5 divided by the sine of 30 is equal to x. And this is what I want to put in my calculator to find that missing side. So I'm not sure if this is exactly what you were looking for with your question, but hopefully that gave you some direction on how we can use the law of sines. I've got looking through the chat, I missed these comments earlier. I am loving seeing people from New York. I'm loving seeing people from Tucson, Arizona. Somebody asking for the law of sines, which we just did. Somebody joined us from Bangkok. That is amazing. Welcome, welcome. We are glad to have you for our office hour to answer your trig questions. Partnering with Chegg, I'm at Wallace STEM. You can find me at Wallace STEM on lots of my channels as well. You can also find Chegg. We're here to help you be successful in your classes, so make sure you're following so you don't miss any of the excitement. So we just did law of sines. I'm not familiar with kinematic problems and dynamics, but Figgy on TikTok was asking about law of cosines. And that seems fitting that we do a law of cosines problem after we've done a law of sines problem. So let's take a look at a law of cosines problem. A problem that people miss a lot in trig is when we've got all three sides of a triangle and we want to find some angle. Let's say we've got 5, 8, and 11 are the two sides. And let's say we want to find one of these angles. We'll call this angle theta. Most people do all right setting up this problem using the formula for the law of cosines. Remember, the law of cosines is a lot like the Pythagorean theorem. A squared plus b squared equals c squared. But the Pythagorean theorem only works for perfect right triangles. If it's not a right triangle, we do a little correction term where we subtract 2ab times the cosine of the angle C. So what's A, B, and C? The angle we're interested in, A and B are either side of that angle, and C is the opposite side. And then this theta, that angle is the angle that we're actually going to work with. So for this formula, it would be 5 squared plus 11 squared minus 2 times 5 times 11 times the cosine of C, or theta, equals c squared, which is the 8 squared. Where people get in trouble, the mistake people made, don't do this. This is bad. Don't do this. They put all of that in their calculator. The problem with putting all of that in your calculator is it violates order of operations because this stuff has to multiply by the cosine before we do any adding and subtracting. Order of operations says we have to do exponents and multiplications before we do any addition and subtraction. So we're going to do the 5 squared. We can even do 5 squared plus 11 squared because there's nothing that's going to be violated there. That's going to be 25 plus 121. That is 146. Minus, then we can multiply these together. 10 times 11 is 110 cosine of theta, and 8 squared is 64. Then we have to solve this like it's a two-step equation. We cannot combine the 146 and 110. They are not like terms. Don't fall into that mistake. Instead, we'll subtract 146 from both sides. When we do, we get negative 110 cosine of theta is equal to 14 minus 6 is 8, negative 82. And then get rid of the 110 by dividing by the negative 110. So the cosine of theta is whatever this fraction is. It's a positive because it's a negative divided by a negative. We could reduce it, but we're going to use our calculators in a minute anyway, so it probably doesn't matter. So on my calculator, I just have to do the cosine inverse of this value, 82 over 110. And whatever that gives me is going to be what my solution is for theta. So thank you for asking about law of cosines. It came so perfectly timed right after the law of sines. All right. Excellent. We got people here from Telsanova. All right. Very cool. Suburbia too. Welcome. Welcome. All right. Well, hopefully that Martina, that question you were asking about, I think there's a piece of information we're missing. Maybe it's a right triangle. Right triangles are easier to solve because we have that extra information. That might help it as well. Hello to Brazil. Welcome. Thank you for joining us. I've always wanted to visit Brazil. Excellent. Thank you. Thank you. So we got some great questions coming in for calculus as well. I see that trig sub question. Those are some of my favorite calculus questions. I do a live office hour for calculus on Thursdays, not this Thursday. We're taking a break this Thursday, but next Thursday, I will be doing it at 4:15. And if you want the full schedule, make sure you're scanning this QR code so that you can make sure we cover that during that office hour. This is all about trig, and there is a little kind of tangent related. See what I did there, that pun? Tangent related to trig with this stuff called hyperbolic trig. And I saw a question from Sarthanic on Instagram. I'm probably saying that wrong. You want me to teach you hyperbolic cosine and hyperbolic sine. I'll give you a really brief introduction to hyperbolic trig versus regular trig. We're not going to go too deep into it because it's a little bit beyond the scope of trig, but it really reinforces some of the concepts of trig as well. So it is kind of neat to look at. The whole idea of trigonometry, the whole course of trigonometry is built on this concept that I have a circle whose radius is 1. And if the circle's radius is 1, any point on that circle will have a height of sine and a length of cosine and a hypotenuse of 1. We end up with this relationship of sine squared theta plus cosine squared of theta equals 1. And all of trig is built on this relationship, and it works great on flat planes. The problem is some people postulate that what if the universe isn't actually a flat plane? What if it's a hyperbola? So we've got this relationship here, where now when we have these weird triangles that are not straight, they've got curved edges on the hyperbola, we end up with the relationship that, oh, I hope I don't get this backwards. Somebody's gonna have to Google this, make sure I'm not doing this backwards. We call it sine hyperbolic squared minus cosine hyperbolic squared of our theta angle equals 1. We change the plus to a minus, and we end up with this hyperbolic trig with these curved-sided triangles, which has some cool geometric properties that are useful to us in a lot of kind of advanced applications. But what's cool is most of the trig properties still hold with this relationship. So we can do the hyperbolic tangent squared properties. We can do the reciprocal properties. We can do all the other properties with hyperbolic trig. And that's kind of a cool little piece. Oh, Martina, it was a right triangle. How did we miss that part? Oh, okay. I want to go back to your question then, because it might be solvable now. That makes a big difference, because if we know that the sine of this angle is 1/2, if we know that the sine of an angle is 1/2, the only angle that's going to give me 1/2 is a 30-degree angle. So that tells me that angle A is 30 degrees. And so, and that's just right off the unit circle, right? 30-degree angles down here. It's got a height of 1/2. That coordinates of that point at 30 degrees is √3/2, 1/2. Sines the y coordinate. So we know that 1/2, 30 degrees. We know that angle is 30 degrees. And if that's angle A, opposite angle A, that's what we call side A. So I think that's the one that you wanted to make 20. And so now what's nice is because sine is opposite over hypotenuse, that means if I set up the sine of our 30-degree angle as opposite over hypotenuse, 20/x, sine we know is 1/2. So I actually didn't even need to know it was a 30-degree angle. We just know the sine of this angle is opposite over hypotenuse, 1/2, but that's 20/x. Well, I can solve this really quick by multiplying the diagonals. 1 times x equals 2 times 20, and I get 40. And so this angle, this side up here, must be 40. So I didn't even need to know the 30 degrees, actually. I just need to know that the sine of this angle is 1/2. Sine is opposite over hypotenuse, so we put the opposite over the hypotenuse. And then since it's a right triangle, we can use the Pythagorean theorem to find this other side. It turns out to be 20 times the square root of 3, and that's related to the cosine having the square root of 3 in there. But that is, oh, maybe it's divided by the square root of 3. Anyways, we can use the Pythagorean theorem and find it. That's what we get for cutting corners. Excellent. So we can actually solve it. I'm excited that we got to the bottom of that. Somebody wants me to prove the, so I don't want to prove that one. I'm going to say no to that one because it's just a long proof and it's very geometric. How about I make a TikTok of it and I'll post it on my page? That might be more entertaining. At Lisa Not Sorry on TikTok is looking at 30, 60, 90 triangles. That's so true. That's exactly what we did. Although what we did could have worked with any relationship, but we have an important property with a 30, that's not the 30-degree angle, this smaller one, so 30, 60, 90 triangle, in that if I know the short side of a 30, 60, 90 triangle, the hypotenuse is always going to be double that, and the other leg is going to be that times the square root of 3. There's another special right triangle we use a lot in trigonometry. It's the 45, 45, 90 right triangle. And with that one, if you know one leg, the other leg is exactly the same length. And the hypotenuse is that length times the square root of 2. And so if I know one side of a 30, 60, 90 or a 45, 45, 90 triangle, we can find the other sides. So here's a 30, 60, 90 triangle, not to scale. Boy, that was really long. That's okay. And let's say I know that this side is 10. 10's too convenient. Let's do 40. Well, 40 is the hypotenuse. That's double what x is, which means 2x is 40. So x then is half of 40, which is 20. The short side is 20. Then the other leg is that x, the 20, times the square root of 3. And so we can quickly find the other sides on that triangle. Now, what's really cool is this is what actually helps us in trig with the unit circle. So if I've got my unit circle on here, we should play a game where somebody keeps track of how many times I say unit circle in this trig review, because everything in trig is built on the unit circle. I'm saying unit circle all the time. Right here, that's a 30, 60, 90 triangle. 30, 60, 90 triangle. I know the hypotenuse is 1, so the short side is half of that. The short side, the y-coordinate, is half of that hypotenuse. The long side is that short side times the square root of 3, and that's how we get the point. Ooh, that green doesn't show up very well. Let me change colors. Equals, so we have a height of 1/2, half of that hypotenuse. And then this long distance is the square root of 3 times that 1/2. Similarly, if I have this point right here on a 45-degree angle, and I know the hypotenuse is 1, we take that 1 and we divide by the square root of 2. And so we've got 1 divided by the square root of 2 on both the x and the y axis. Now, if you rationalize those denominators, you end up with your root 2 over 2. And so you go around the circle, and all of these special right triangles are what actually build the unit circle and all the points. That's why they are what they are. They're all 30, 60, 90 triangles. Excellent work. Martine's counting my unit circle count. I think we're up to 24. Now I'm at 25 because I said it again. Too fun. Excellent. Can tau do some substitutions? That's a great question. So I want to talk really briefly about tau. I don't want to spend a lot of time on tau because it's probably not on your trig exams, but it is kind of a cool concept. There's a great video out there by Hart that she made years ago that you can check out that really dives into tau and why it's better than pi. We use pi all the time because it's familiar to us. Pi on the unit circle, there's another one, are you counting? Pi on the unit circle is halfway around the circle. Why? Because we said, okay, well, if the diameter of a circle is related to the circumference of the circle, because the circumference is the diameter times pi. But then we decided randomly that we don't like diameters, we prefer radiuses. And so the radius, I meant to go with a different color, let's go with blue. The radius r, there's 2 radiuses in a diameter. So the circumference became 2 radiuses times pi. And so 1 pi is only halfway around, and the other pi gets you the other way around when the radius is 1. Everything is based on the radius of the circle, and the radians going around the circle. But what if, instead of saying 2 times pi times the radius, what if we said that the constant we are interested in was tau, not pi? Notice it's got 1 leg, which is kind of funny because it's kind of like a half a pi, but tau is actually 2 pi's. Tau is equal to the circumference around the circle, 1 circle. And it actually makes some things make a lot more sense, which is kind of funny because if 1 tau is all the way around the circle, then tau over 2 would be halfway around the circle, and tau over 4 would be 1/4 of the way around the circle, and tau over 8 would be 1/8 of the way around the circle. And that kind of seems like it would make more sense. The problem is pi was already so popular that pi wins just because of popularity and familiarity. That's what branding can do for you as a business, I guess. So tau never, ever caught on, unfortunately. All right, well, excellent. Well, I digress. I got a little bit off topic. Coming back, this is your office hour to answer your questions about trigonometry. So what trig questions do you want to take a look at? Do you want to look at graphing of trig functions? Do you want to look at more proofs? Maybe solving trig equations? Maybe working with inverse trig functions? What trig property, law of sines, law of cosines, radians, what do you want to take a look at? Stick it in the comments and we will take a look at it. One question came in from Brooklyn on TikTok. Can I explain solving the ambiguous case of triangles with the sine law? That is an excellent question. It is one that is often missed by students. So let's take a look at an example of an ambiguous triangle. So let's say this is some triangle and it is not to scale. That's really important for the setup. It is not to scale. This might be really small. This one might be really long. It is not to scale, so don't be fooled by that. And let's say I know this side is 5, and this side is 3, and this angle is 20. And we are asked to find this angle right here, theta. Well, the law of sines, which we said earlier, the law of sines says we can take any angle and its opposite side, and they should be proportional. If I take the sine of the angle and divide by the opposite side, That's going to be the sine of any other angle. And I divide by the opposite side. And this seems like all I have to do is multiply both sides by 5, and we get 5 sine of 30 over 3 is equal to the sine of theta. And this is where our calculator comes in. I try to not spend time on the calculator because it's kind of boring to watch me push buttons on the calculator. 5 sine of 30 divided by 3 is 0.83333. So then if I want to figure out what theta is, we should just be able to take the sine inverse of this function. So when I do the sine inverse of this answer, if I can type it in correctly, I end up with theta is equal to 56.4 degrees. And so a lot of students will say, okay, that angle's 56.4 degrees, we're done. No, we're not. This is where the ambiguous case comes in, and it actually goes back again to the unit circle. Everything's related to the unit circle in trigonometry. Back on the unit circle. Grab an orange here. Does that orange show up? That's not that good. Where did the 30 come from? Ah! Good catch, Rob. Copying is sometimes the hardest skill of mathematics. I copied a 20 and wrote 30. Well, geez. Good catch. That's 20 degrees, which means my calculations are all wrong on my calculator. Let's go back to that. Thank you. Sine of 25. Sine of 20 divided by 3 is actually 0.57. Good catch, good catch. Keeping me honest here. I often tell students, if you can copy the math problem right, you've already done half the work. We're going to do the sine inverse now of 0.57. And when I do, I get angle theta is actually 34.8 degrees. All right, good. Thank you for catching that. I appreciate you all keeping me honest. All right, so theta is 34.8 degrees. That's in the first quadrant. That's a 38, 34. I'm transposing numbers now. I'm getting in more trouble. That's 34.8 degrees. The problem is, as we said, this is where sine is 0.57. This y coordinate, this distance here, is 0.57. But that's not the only place on the circle where that height can be 0.57. I can move that height down here, and I can hit the circle again, and I can have a height of 0.57 on this angle over here. In other words, this angle, the coterminal angle here, is also 34.8 degrees, which means the obtuse angle, erasing this one now, getting it out of the way, the obtuse angle is also a candidate for our angle theta. So we have to consider that obtuse angle. Well, what is that obtuse angle measured to? Well, if I went halfway around the circle, that's 180 degrees. Then we're going to back up 34.8 degrees to get to our other angle. So that's 180 degrees. And we'll back up 34.8 degrees. That's going to give me 2.9 minus 4 is 5. 7 minus 3 is 4. 145.2 degrees. Make sure that's right. 79.81. Yes, Kira's. So that means this angle theta here, we don't know if that angle is 34.8 degrees or if that angle is 145.2 degrees. There's two possibilities, which is why it's so important that I mentioned this is not to scale. That looks like an acute angle. It's not an acute angle. It might be the obtuse angle. Your calculator with sine inverse will always give you an angle that is an acute angle. If you do sine inverse, you have to consider the possibility that there's an obtuse angle. And so that obtuse angle is the 180 degrees minus the acute angle to get the angle that might be your ambiguous case, your hidden triangle. So hopefully that helps there. with that one? Great question. Look at the questions that are coming in. Remember, these are your questions because we're doing your review session, your office hour with Che and at Wallace STEM. So hopefully this has been helpful to you. We've still got a few minutes left to do a couple more problems. One question came up asking about radians. So let's just radians, please. Let's talk about how I remember the radians on the unit circle. Hopefully this will help you remember radians on the unit circle as well. A lot of the time students tell me they really like working with degrees. On almost every problem, they're converting radians into degrees because they like degrees better. The reason you like degrees better is you learned them first. There's no other reason than that. You're just familiar with a 90-degree angle. You know what a 90-degree angle is. You know what a 120-degree angle is. You've done that before. You're familiar with it. With radians, I need you to take the time to get familiar with radians too, because once you get familiar with radians, you're going to actually like them a lot better. I promise. Students never believe me, and then by the time they get to the end of my trig class, I have drank the Kool-Aid and are now radian believers. So I am going to promote radians. And the way I help remember my radians is I think about my unit circle like I think about a clock. At a clock, you've got noon, 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock, 5 o'clock, 6 o'clock, 7 o'clock, 8 o'clock, 9 o'clock, 10 o'clock, 11 o'clock, and back to 12 o'clock. Those are your key points on the unit circle, and they count by 6. So if I can remember 1/6 is here, 2/6 is here, 3/6 is here, 4/6 is here, 5/6, 7/6, 8/6, 9. Whoops, what happened? I missed the number 6. Counting is hard. 6, 7, 8, 6, 9 pi over 6, 10 pi over 6, 11 pi over 6, and 12 pi over 6. And you've got right there basically almost all of the unit circle. Now, some of these fractions can reduce. 2 pi over 6 can reduce to pi over 3, for example. And 3 pi over 6 can reduce to pi over 2. And 4 pi over 6 can reduce to 2 pi over 3. 6 pi over 6 can reduce to pi. 8 pi over 6 can reduce to 4 pi over 3. 9 pi over, that's a 6. It's the ugliest 6 I've ever drawn. 9 pi over 6, that's going to reduce to 3 pi over 2. 10 pi over 6, that's 5 pi over 3 when I reduce, and 12 pi over 6, that's 2 pi. And that's going to give you your thirds, your halves, your wholes, all based on the clock. The only thing that's missing from the clock are the quarters. That's the only thing that's not on the clock. So the way we get the quarters is we're going to mark our quarters on here, a quarter of the way around the circle. And all of those quarters that I marked are the odd quarters. It is odd that normally we do the quarters like here on the axis. It's odd because it's slanted slightly. So I'm going to put the quarters on the inside. This is 1 quarter odds, remember. So I'll go 3 quarters, 5 quarters, quarters are 4, and 7 quarters. And those are the odd points. And you've got your entire circle in radians. So that's how I remember it. I literally think about a circle, a clock. Where are the hands on the clocks? That's going to give me all the 6 halves and thirds. And then the quarters, those are just right in the middle. And those are all the odd numbers, 1, 3, 5, and 7. So hopefully that helps you remember your radians. They are very important to being successful in calculus or in trigonometry and beyond. These come up a lot in calculus. They come up a lot in differential equations. They come up a lot in physics. They come up a lot in everything else. They are really important. And a great question came in from Drew. Thank you for the question on YouTube. What if they don't break? Why? What if they don't break down evenly? that's when you're going to have to start using some of your properties. So for example, using our unit circle, let me get the unit circle out of the way here. So we can do, like, let's say I want to know about pi over 12, which is right here. Pi over 12 is not one of our key points on the unit circle, but we can still figure out what that pi over 12 is. And a great comment came in as we're looking at this. Key is to remember the first quadrant. You're exactly right, because if you can remember the first quadrant, everything else is kind of a reflection of those quadrants flipped over and flipped over. That helps as well. Let's look at pi over 12, though. There's a couple ways that we could handle pi over 12. We want to find the sine of pi over 12. That's going to be the y-coordinate. And the cosine of pi over 12. That's going to give us the x-coordinate of that point. Now, one way to think about pi over 12 is pi over 12 is 2, oh, it's 1/2, sorry, 1/2 of pi over 6, right? And we have a trig identity for the sine of 1/2 of an angle. The sine of 1/2 of an angle is equal to, plus or minus, depending on which quadrant we're in, but this is the first quadrant, so it's going to be positive, the square root of 1 minus the cosine of the angle divided by 2. So in our case, this is going to be the square root of 1 minus the cosine of that half angle, cosine of pi over 6, all over 2. Well, what's the cosine of pi over 6? Great question. It goes back to our unit circle. Pi over 6 is right here. Cosine's the x-coordinate. That's a 30, 60, 90 triangle. The x-coordinate is root 3 over 2. So this is root 3 over 2. We have the square root of 1 minus the square root of 3 over 2. And then the whole thing is divided by 2. A little bit of simplifying to get rid of the funny fraction. I'm going to multiply by 2 all the way across on top and bottom. And sine is the square root of 2 minus the square root of 3 over 4. This is the y-coordinate of pi over 12. So we can find ones that don't come out evenly using the angle formula, the half angle formula. For cosine, the formula for cosine of a half angle is very similar. Half of the angle theta. The only difference is instead of a minus here, there's going to be a plus there. So it's the square root of 1 plus the cosine of theta over 2. So if I want to evaluate the cosine of pi over 12, that's the cosine of 1/2 of pi over 6. Well, using our formula, that's the square root of 1 plus the cosine of theta, or not theta, in our case, pi over 6, and all over the 2 from the formula. And the same thing's going to happen. Cosine of pi over 6 is still root 3 over 2. And then we're going to multiply by the 2 again. It's going to give us the same radical. The only difference is now there's going to be a plus here from the formula instead of a minus. And this is the x-coordinate. So we've got our x-coordinate and our y-coordinate of pi over 12 if it doesn't go in evenly to one of our key unit circle points. Excellent. Drew, hopefully that was helpful. Clarifying what you did in class with those when they don't come out evenly. That's why we have all of those properties. We have other properties too to help us with like the sum and difference. If we can have angles that add to a value, that can help us with those evaluations as well. I'd love to do one of those, but we are just about out of time. So quick question came in from Math Lover though. What about the plus or minus? That plus or minus has to do with what quadrant we're in. So if you're working with sine in the second quadrant, sine in the second quadrant is negative. You've heard that all students take calculus. That tells us who is positive where. Everything's positive, sine's positive, tangent's positive, cosine's positive. Which means if I'm dealing with an angle over here, If I'm dealing with an angle over here, the sign is positive because I'm going up, so we're going to do the plus. If I'm dealing with an angle down here, the sign goes down, you're in the negative, so that's going to be a negative. So that's why the formula has plus or minus, because the formula doesn't know what quadrant we're working in. So you have to look at the quadrant, decide is it positive or negative. But great questions coming in. I'd love to answer all of them. In fact, next week when we do some trig, maybe we will take a look at doing some of that sum and difference formula stuff. So make sure you scan this QR code so you know when the lives are going to be next week for trig, for calculus, for pre-calculus, and algebra, economics, chemistry, physics. Scan the QR code, follow us here, follow Chegg on TikTok, follow Chegg on Instagram, follow Chegg on Twitch, follow Chegg on YouTube. Thank you for joining us, but we are out of time. It goes so fast because it's so much fun doing these reviews with you. I look forward to seeing you next week on